Okay, so the purpose of this video is to go through this 21B integration flow chart, for lack of a better word. The idea basically being that we're going to talk about what to do when you see a certain type of thing. So first and foremost, I'm going to break this into two or three videos, probably three. We're first going to go through the algebra sections, meaning if you see something that is algebraic, meaning kind of just powers of x, square roots, other roots, but no trig, no exponentials like e to the x, no logarithms or inverse trig. So if you just see something that's algebraic, what do we do? Well, there's a whole bunch of options. So let's kind of go through. All right, so I've got a whole list of integrals here. So the first part of this is, can you make it an exponent problem? I mean, can you just write it as powers of x? So this is for integration flowchart. And part one, if we see something that's algebra. So no trig, no e to the x, no logarithms, no inverse trig. None of that is in. All right, so part A, can you make it an exponent problem? And I'm really just going to read through this so that we get the words here. Meaning, so when I say exponent, I mean a power of x. So e to the x, I call an exponential. An exponent problem, I'm really thinking of x to a power. So maybe I should call it an exponent problem. That's a better word would be a power problem. So by a power problem or an exponent problem as written in this handout, I mean an expression which may be written as the sums or differences of terms in the form a times x to a power, where the powers are constants. So for example, we might try an example if I can get them easily. The integral of 3x plus 5 squared. We can totally multiply that out. 3x plus 5 squared is equal to 9x squared plus 15x, 16x is 30x plus 25. And that's really straightforward to integrate. We can just, put this in there. That's going to be 9x cubed over 3 plus 30x squared over 2 plus 25x as a constant, which we could simplify as 3x cubed plus 15x squared plus 25x as a constant. You can get higher powers, but if powers get too high, it usually becomes easier to just a substitution we'll talk about next. But for example, if I was going to do the integral of 2x minus 1 cubed, this still to me feels reasonable to multiply out. And there's this whole 1, 3, 3, 1 pattern in 3 cubic powers, Pascal's triangle. We're getting the integral of 1 times 2x cubed plus 3 times 2x squared times -1 plus 3 times 2x to the first times -1 squared plus 1 times -1 cubed, which simplifies to 8x cubed plus 3 times 4 is 12x squared, so it's minus 12x squared plus 6x minus 1. And then we integrate and we get 8x to the 4 to the 4 plus 12x cubed. We have to pick very nice examples where things come out nicely, but it's kind of by accident. Plus 6x squared over 2 minus x plus c, and I lost my minus sign again because I wasn't being careful. And then this would simplify to 2x to the 4th plus minus holy smokes 4x cubed plus 3x squared minus x plus c. One more example of this kind of making it an exponent or a power of x problem, an exponent of x, I suppose, would be if you have something that's like a rational expression where the denominator is just one term. So for example, the integral of 6x to the 4th plus 5x cubed minus the square root of x all over 2x squared. Since the denominator has a single term, you can divide each numerator part by that number. So I can rewrite this as the integral of 6x to the 4th over 2x squared plus 5x cubed over 2x squared minus, I would rewrite that as x to the 1/2 over 2x squared. I probably would have factored out the 1/2, but too late now. So I'm just going to simplify this as the integral of 3x squared plus 5 times x minus 1/2, and x to the 1/2 over x squared. We subtract those powers, and 1/2 minus 2 is a negative 3/2. So we get x to the negative 3/2. Then we use the anti-power rule as we have been. We're going to get 3x cubed over 3 plus 5 times x squared over 2 minus 1/2. And the antiderivative of x to the negative 3/2 is x to the negative 1/2 divided by negative 1/2 is the same as multiplying by negative 2 over 1. And then simplifying, we get x cubed plus 5/4 x squared. Minus and minus is plus, and those actually cancel. You just get x to the negative 1/2. Cool. Right, that works out. Okay. So let's look at the next kind of section of this, which is, does the derivative of one part equal another part? And again, we are only focusing on just algebraic things, meaning powers of x. So you're kind of limited here. You could have something like the integral of 2x over x squared plus 1. And then you would let, different color here, you would let u equal the x squared plus 1. Because the du is exactly 2x dx. So then we would rewrite this as the integral of du over u, which is going to be, if you prefer, the integral of 1 over u du, which is the natural log of the absolute value of u, which is the natural log of the absolute value of x squared plus 1. I picked this example specifically because it kind of comes up a lot. Well, let's look at a few other examples. You could have something like the integral of x squared times x cubed plus 5 to the 99th power. And then we would let u equal the x cubed plus 5, because the du, the derivative of that part is 3x squared dx, and we essentially have that. Right? The derivative of one part is the other part. I've got an x over it. So basically, with these powers of x, if you see one part and another part whose power is 1 less, that's usually a good sign that, oh yeah, you said it's probably negative here. So here we would say that then 1/3 du equals x squared dx. That's the way I prefer to do it. So then this integral is going to equal, well, the x squared times dx is going to become the 1/3 du. Right, that's my 1/3 du. And then the rest is just u to the 99th power. When we're doing a u sub, every x has to turn into u. Specifically, the dx must turn into du. So then we get 1/3 u to the 100th power over 100, and the plus c, and that's going to be u to the 100th over 300. And then if it's an indefinite integral, with all these examples are going to be indefinite, we have to change back to x. So we're going to get x cubed plus 5 to the 100th power over 300. Let's do a couple more examples. Sometimes it's a little less obvious. For example, let's not quite do it. Let's say we have something like the integral of 2x plus 5 over I'm making this one up on my way. Let's say we have 4x squared plus 20x plus 9. Here it might be a little less obvious, but I'm definitely going to check if I let u equal the denominator. It certainly seems like its derivative could be related to the numerator. And if I check that, the du is equal to 8x plus 20 x, and I can factor out in 4. Yep, I need to write it. So du is going to be 4 times 2x plus 5 dx. And I exactly have a 2x plus 5 dx. So this right here, that's going to equal my du divided by 4, which I guess I could do that. Du divided by 4 is equal to 2x I rewrite my integral, the du over 4, or the 1/4 du. I always like to bring this constant out in front, so the 1/4 is going to live out in front. The du I put at the end, and then I'm going to have, I could have put the du on top. If I didn't, I'm going to put a 1 on top, because 1 times du. And then I have a u on the bottom. So again, I'm going to get a natural log. That's going to be 1/4 the natural log of the absolute value of u plus c, which is going to be 1/4 the natural log of the absolute value of 4x squared. That's 20x, that's 9. Something that comes up in the u substitution situation is what I like to call the idea of mini u substitution. So this is a little bit of a divergence from the handout, but I did think it's worth covering. So something that comes up, quite often is something like, also I will point out there's lots of, I'm doing different examples that are on the handout. The handout also has good examples that are worth reading through. But again, when you're doing a u sub, you're really looking to pick a u whose du is also in there. And for powers of x, it's really kind of just like, you have x to the 5th, you're hoping an x to the 4th is also in there. So there's a derivative of x to the 5th. Just throw the thing on the ground. So, but if you want to address the idea of what I call a mini substitution. So someone could ask you, do the integral of e to the 4x. And you could do a u sub. You could let u equal 4x. The du is going to be 4 dx. And again, I don't really care that I'm off by a multiple. I have 4 times 1 times dx. So the du divided by 4, or 1/4 du is equal to dx. You can always let u be a multiple of x, because the du will always work out. The du can just be a constant times dx. So rewriting this, it's going to be the integral of, well, my dx is 1/4 du, and my e to the 4x is now e to the u. The integral of e to the u is e to the u. I could put the plus c in here, but that seems kind of silly. And then we end up with 1/4 e to the u plus a new constant 1/4 times c, is another constant c. And then e to the u is really e to the 4x. But the point I want to make is that if you know that taking the derivative of something, not the antiderivative, the derivative of something will make you multiply by a constant because of the chain rule, right? So I know, and you know, that the derivative of e to the 4x is e to the 4x times 4 because of the chain rule. Then the antiderivative of e to the 4x is going to make you divide by that same constant. You're going to get 1/4 times e to the 4x. Because the derivative of e to the 4x is e to the 4x times 4, but I want the derivative of this to be just e to the 4x, because I want to find the antiderivative of e to the 4x. And since the derivative of 1/4 e to the 4x is 1/4 times e to the 4x times 4, the 1/4 and the 4 cancel, and you get exactly what you wanted. The sum up to that story is that if we're trying to integrate something into a function you know how to anti-differentiate, and instead of x, you have a multiple of x, then you can easily just divide by that multiple of x. Let me throw a few more examples at you real quick. So, for example, the integral of cosine of 6x is sine of 6x, but not times 6, divided by 6. Or if you prefer, and I do prefer, 1/6 times sine of 6x. And that's again because of the chain rule, because the derivative of 1/6 times sine of 6x plus c is, well, the 1/6 hangs out. The derivative of sine of some stuff is cosine of the stuff times the derivative of that stuff, and the derivative of 6x is 6. Derivative of c is 0. And then that's just equal to, the 6 and the 1/6 cancel, and you exactly get cosine of 6x. As you should, because if you take the derivative of your antiderivative, you should end up back where you started. But that's always why we are doing it. So if you, the thing I really want you to remember is you're doing a mini substitution, which we're actually not mini sub. The idea is that since your derivative would make you multiply by a constant, the antiderivative would make you divide by the same constant. Another example could be, say, the integral of, I don't know, sure, the derivative of secant squared of x over 5. Or if you prefer, and I kind of do, the integral of secant squared of 1/5 x. Well, I know the antiderivative of secant squared of x is tangent of x. So the antiderivative of secant squared of a constant times x is going to be secant squared of that. Sorry, not secant squared, apologies. Tangent, right? The antiderivative of secant squared is tangent. The antiderivative. So the antiderivative of secant squared of this stuff is tangent of that stuff, but then I have to divide by the multiple of x, so divided by 1/5. Or in other words, making this nicer, 5 times tangent of 1/5 x. Again, right, the derivative of this would be 5 times the tangent of the stuff, and secant squared of the stuff times the derivative of the stuff, and the derivative of that stuff would be 1/5. A couple more mini use subs just because I think they're worth a while. There we go. Yes, maybe 2 or 3 more. So the integral of sine of 7x minus 2. Well, again, I know the derivative of sine of 7x minus 2 is making multiply by 7, so the antiderivative is making divide by 7. A negative cosine of 7x minus 2 divided by 7. Or if you prefer, a negative 1/7 cosine of 7x minus 2. Few more examples. Integral of, say, 1 over negative 2x plus 3. That's a natural log. The antiderivative of 1 over x is the natural log of the absolute value of x. The integral of 1 over a linear function of x is just going to be the natural log of the absolute value of that linear function of x. But then if I were to take the derivative of this, I can multiply by a negative 2. So I need to divide by a negative 2. Or multiply by a negative 1/2. Right? Again, you can check. I have no check. If I take the derivative of negative 1/2 times the natural log of the absolute value of negative 2x plus 3, I'm not going to write the plus c. The negative of plus c is 0. And then we get negative 1/2 times the derivative of the natural log of some stuff, chain rule, is 1 over the stuff times the derivative of that stuff, which is exactly negative 2. And oh yeah, that connected with that. One more example, and this actually does come up, I feel like, fairly often in your partial fractions. So the integral of something like, well, I'll start off with this example first. The integral of, say, like 2x plus 6 to the 100th power. You could totally do the u set here. U equal 2x plus 6. And then your du is going to be 1/2, or dx is going to be 1/2 du. But I don't really need to do that because I know that I'm essentially integrating u to the 100th power. Great, I'm going to get u to the 101 power over 101. And then I know my u is actually 2x plus 6. But then I also have to divide by 2. So I took the derivative of this, I would get 101 times my stuff to the 100 power divided by 101, but then I'll do my part. The derivative by 2. But I don't want a 2, so I have to divide by. And then you can simplify that. 2x plus 6 to the 101st power over 202 plus c. No, if you were going to check this, you shouldn't use the quotient rule. Right? The derivative of a fraction where the denominator is just a constant, you can either, well, I would just say it's 101 times 2x plus 6 to the 100th power times the derivative of 2x plus 6, which is 2, all over 202. And then, oh yeah, exactly 202 cancel 202. If you prefer, you could also rewrite it as the derivative of 1 over 202 times 2x plus 6 to the 101st power. And then the derivative is exactly the same thing. That's 1 over 202. And the derivative of this to the 101st is 101 times 2x plus 6 to the 100th power times 2. And again, the appropriate things. One more example, I'll squeeze in here, and I won't do all the work for. If you're integrating, say, like 1 over 3x plus 1 to the 7th power, I'm gonna rewrite it as the integral of 3x plus 1 to the negative second power. But then I'm just gonna use, again, the same idea. I'm gonna get 3x plus 1 to the negative 6 divided by negative 6 and also divided by the coefficient of x, just 3. And then I write this as negative. I would probably write it as negative 1 over 6 and 3 is 18, and 3x plus 1 to the negative 6 is 3x plus 1 to the positive 6 in the denominator. That's how I would probably choose to write it. This kind of thing comes up a lot in partial fractions because you're often integrating something raised to a power in the denominator, and it's usually a linear thing, so it's easy to do this. Okay, I know I said that's a lot about substitution when you're dealing. Oh, and so I guess I did throw in some examples that were trig because I was trying to give examples of this mini substitution stuff. But so the mini substitution idea applies for algebra and for trig. So sorry, I kind of stepped out of where we were doing, but that's fine. So back to the algebra section is like the longest section, so we're going to get through it here. So far we've talked about, again, just the first two things. We've talked about on this handout, can you make an exponent problem, so powers of x, and does the derivative of one part equal the other part? So use substitution. Powers of x, you're really just looking for one part to be one less power than the other part. And there's some good examples here as well. So then after that, we kind of get to the tricks section, which I know seems like we didn't really talk a lot, but there's a lot of quote unquote tricks. And I guess I missed, sorry, the substitution section was section B. Okay, go back and label this. I'll probably post these notes as well, as well. So I go back here, one section. So there's I guess I labeled that part 2. Sorry, the labeling here is maybe less than excellent. Let's see. That would be part 2, but the part 2 is the trig section. So I guess this is not 2. Sorry, this is B. Which, yes, we spent a lot of time on that. That's all right. All right, so then moving on to part C, which is the tricks. And there's a lot of quote unquote tricks. Tricks. And again, we're kind of spelling things out in order of what you should try. Meaning, if you have powers of x or algebraic things more generally, you should first try, can I just simplify it as x to the power, x to the power. If I can't do that, can I do it? If I can't do that, then I should try the next trick. So the next trick is long division. So I wrote myself lots of examples, that'd be great. So long division. I didn't actually do this example on my own, so hopefully it turns out not terrible. Cool. So the first trick is long division. And we do the long division if you have a rational function and the degree of the top is greater than or equal to, people sometimes forget about the equal to part, the degree of the bottom. So we'll do 2 examples here. The first, the integral of x to the 4th plus x with x minus 2. Here the degree on top is much larger, so we're going to do the long division or the polynomial long division. So we're going to do x minus 2 into, and when you write out the dividend, or the thing that's being divided into, which also is called I think it's called the dividend, and that's the divisor. We're going to write all the missing powers of x. So x to the 4th plus 0x cubed plus 0x squared plus 0x. You don't need to actually write the 0 at the end. You could have wanted to. And then we ask ourselves, what do you multiply by x to the 4th? And the answer is x cubed. And then you multiply x cubed by all of this. So you get x to the 4th minus 2x cubed. Subtract. That minus that is always going to be 0. That's why we chose it the way we did. And 0x cubed minus 2x cubed is plus 2x cubed. Bring them the next term. That shouldn't be a 0x, so that should be a 1x. Sorry. Right, because it's an x to the 4th plus x. Something like that. So then we do it again. So what do you multiply by x to get 2x cubed? 2x squared. 2x squared times x is 2x cubed. 2x squared times minus 2 is minus 4x squared. Subtract. That minus that 0. 0x squared minus 4x squared is plus 4x squared. Bring down the x. Do it again. X times 4x is going to give me 4x squared. So 4x times negative 4x squared. 4x times negative 2 is negative 4x. Track. I might want the 0 there. I don't probably need it. That minus that 0, and x minus 4x is plus 5x. And then sure, bring down the 0. Not that you really need it. X times 5 is going to give me 5x, so I get 5 times x. And then 5 times minus 2 is minus 10. I don't think you really need the 0 there to see that, but you get this times that 0, and 0 minus 10 will just x times that is 10. So then after you've done all this polynomial division, you have to rewrite the integral. So the integral is going to equal the integral of the quotient plus the remainder divided by the divisor. Right? Because when you're dividing x to the fourth plus x by x minus 2, you're saying that x to the fourth divided by, or x to the fourth plus x divided by x minus 2 is equal to this amount here. But then there's still this leftover part that needs to get divided by x minus 2, which we're not going to do. We're just going to write it as 10 divided by x minus 2. So this integral of x to the fourth plus x over x minus 2 is equal to, let's see here. So we've got, sorry, the integral. I still have to do the integration. We're just rewriting the integrand. X cubed plus 2x squared plus 4x plus 5 plus 10 over x minus 2. So then we're going to integrate and we're going to get x to the fourth over 4 plus 2x cubed over 3 plus 4x squared over 2 is 2x squared plus 5x plus 10 times the integral of 1 over x minus 2 is the natural log of the opposite value of x minus 2. Let's see. That's it. So long division is pretty nice. A lot of the times a long division problem will then, after that, you'll end up doing a partial fraction problem because the denominator will be more complicated than sometimes. Let's look at one more example of long division, though. At least one more example that doesn't involve partial fractions. But one where the degree on top and the degree on the bottom are the same. So let's say we had something like the integral of, and I'm going to make it not too terrible here. Yeah, let's do something. I'll do something kind of obvious-ish. Here's a pretty common example of the integral of, like, say something like x squared plus 4 over x squared plus 1. So this one, you can do this, like, people do this usually using like a trick often, but the more general kind of safe way of always doing this is just doing long division. So the trick is to write this as x squared plus 1 plus 3 over x squared plus 1, and then to break it up as x squared plus 1 over x squared plus 1 plus 3 over x squared plus 1. And then you're just getting the integral of 1 plus 3 over x squared plus 1. But really, you've done the long division here. You just haven't written it out. If you do x squared plus 4 divided by x squared plus 1, it's kind of silly. But if you do x squared times what equals x squared, oh, it's a 1. 1 times x squared is x squared. 1 times 1 is 1. Subtract 0. 1 minus 1 is 3. So yeah, the integral is going to be exactly 1 plus 3 divided by x squared plus 1. Exactly that. And then that's going to be, I'm going to break this up just to make it super obvious. The integral of 1 plus 3 times the integral of 1 over x squared plus 1. That's going to be x. And that's going to be 3, plus 3 times the arc tangent. I will also point out, just because it's worth pointing out, I'll do one more example. One more. Because there's one more kind of thing that comes up. If you were going to do, say, the integral of 2x minus 5 over x plus 4. So in this sort of example, you can either do long division, specifically when it's a degree 1 thing over a degree 1 thing, or you can also do a use over the backside. So long division, and I think the long division is actually easier. So first way, long division. So 2x minus 5 divided by x plus 4. X goes into 2x 2 times. 2 times x plus 4 is 2x plus 8. Subtract. Minus 5 minus 8 is minus 13. You be careful with the subtraction if you usually miss the signs. So we're going to rewrite the integral as the integral of 2 minus 13 over x plus 4. And that's going to equal to x minus 13 natural log of the opposite value of x plus 4. Let's see. 13, not a b. Sorry, sometimes my b's and 13s look interchangeable. But I have 13, not a b. Alternatively, we could do a u sub. We could let u equal x plus 4, du will equal dx, and then we solve for x. So u minus 4 is equal to x. So we rewrite the integral 2x minus 5 over x plus 4 dx as well. The x plus 4 is u. I didn't do that wrong, but whatever you should always do for my own advice is whenever you're doing a u sub, you should always make sure the dx changes into du before you do anything else. So first I should have been like, oh, my dx just automatically is u, so we put each other. Then my x plus 4 is u. And then I'm going to replace the 2x here with a 2 times u minus 4. This ends up being, if I simplify this, the integral of 2u minus 8 minus 5 is minus 13 by u. And then I'm going to rewrite this. I'm going to divide these things like I did. Like this is kind of like back to part A, I think, where if you can write it as powers of your variable, you should. So 2u divided by u is just 2, and 13 divided by u is 13 divided by u. We're going to get 2u minus 13 natural log of the absolute value of u. And then plugging back in what u is equal to, I'm going to get 2 times x plus 4 minus 13 natural log of the absolute value of x plus 4. Let's see. And I'm going to multiply this out just to show a slight difference. This is equal to 2x plus 8 minus 13 natural log of the absolute value of x plus 4. Let's see. And yet my answers do differ. They actually don't really differ. It's just that this constant here is C1, and this constant here is C2, and C1 is equal to C2 plus 8. But these do look like they differ by a constant. And sometimes when you use a different method of integration, your answers are going to look like they differ by a constant. Happens sometimes. All right, let's move on to the next section, which is partial fractions. The partial fractions could take a long time to talk about, but okay. So partial fractions. To do partial fractions, you have to have a few things being true. It has to be a rational function, first of all. So we need to be a rational function. Sometimes you'll have other things that start off as not rational, and then you do use something to become rational. But you have to have a rational function, meaning a polynomial over another polynomial. It has to be, the degree on the bottom has to be strictly bigger than the top. So the degree of p of x must be smaller than the degree of p of x. If it wasn't, you would do polynomial division first, just like we talked about. And then finally, the denominator must factor. So, for example, you might have something like the integral of 2x plus 5 over x squared plus 4x plus 3. And I've said many times, before you do anything like this, I should check for a u sub. If that was x squared plus 5x plus 3, the u sub would totally work. That would be u plus x plus 5x plus 3. It doesn't here because my du would be 2x plus 4 and I have to check for 5, and it's just not going to work out. So then I say, oh, well, the degree on top is less than the degree on the bottom, and the bottom does factor. So I'm going to write the partial fraction decomposition. That bottom factor is x plus 3 times x plus 1. And that's going to equal a over x plus 3 plus b over x plus 1. Then I'm going to multiply both sides by the common denominator. I'm going to get that 2x plus 5 is equal to a times x plus 1 plus b times x plus 3. And then multiplying both sides by x also times x plus 1. Here that's canceled. Here the x plus 3 cancels and get x plus 1. Here the x plus 1 cancels 2 x plus 3. And now there's kind of what I call a two-pronged attack for this. The first thing you should do whenever you're trying to solve for the constants in your partial fraction decomposition is pick nice values of x. So I'm going to pick x equal to -1. Essentially values of x that mean something 0. So on the left-hand side, I get -2 plus 5. On the right-hand side, I get a times 0 plus b times -1 plus 3. I get that b is equal to 3 times. Take x equal to -3. I get -3 times 2 plus 5 is -1. equals a times -2 plus b times 0. So a is going to equal positive 1/2. So then I can rewrite this integral as the integral of 1/2 over x plus 3 plus 3/2 over x plus 1, which is going to be 1/2 the natural log of the absolute value of x plus 3 plus 3/2 the natural log of the absolute value of x plus 1. Let's see. I would leave it like this. Sometimes textbooks do something funky and like bring these up as powers and then combine the natural logs. So you could totally write this as the natural log of the absolute value of x plus 3, the 1/2, plus the natural log of the absolute value of x plus 1, 3/2 plus c, and then combine those as the natural log of the absolute value of x plus 3 over 1/2 over x. Sorry, not over, times, apologies. Natural log of x plus 3 over 1/2 times x plus 1. I wouldn't normally do that or even think about it, but sometimes textbooks will write weird answers like that. So just be on the lookout for specifically simplifying things with logarithms. Sometimes textbooks do weird things. Let's look at one more example. I don't want to get too deep into the partial fraction rule because there's lots of things that happen. Well, let's look at one more example that kind of shows a couple of different things. Yeah, sure. So let's do the integral of 3x minus 2 over x cubed minus 6x squared plus 9x dx. Again, does not do a u substitution. So what we're going to do instead is see that the degree on top is less and the bottom does factor. So we're going to write this as the integral of 3x minus 2 over x times x squared minus 6x plus 9 is x minus 3 squared. So then I have that 3x minus 2 over x times x minus 3 squared. So since I have a repeated, because it's the second power, linear factor, x minus 3, I have to have that highest power and then the lesser power. So I'm going to have a over x plus b over x minus 3 squared plus c over x minus 3. I like to write the highest power first and then write the lower ones after. Some people like to start at the lowest power and just work their way up to that. It does not matter which order you do it in. Then multiply both sides of this equation by x times, I shouldn't write times like that. I'm going to write times like this. X times x minus 3 squared. Then we're going to get 3x minus 2 on the left equal to a times x minus 3 squared plus b times x plus c times x minus 3. And again, just like before, we're going to use the convenient value of x. So picking x equal to 0 is going to make this term 0 and this term 0. So I'm left with -2 on the left and a times 0 minus 3 squared on the right. So that's a times 9. So -2 divided by 9 is equal to a. Then we pick x equal to 3 because that's going to make this 0 and this 0. So 3 times 3 is 9 minus 2 equals a times 0 plus b times 3. So 7 over 3 is equal to b. And then finally, so I've run out of convenient values. There's no other choice for x that will let me solve for, that will make lots of things 0. So you have two different options here. My personal preference is to do what's called equating coefficients. So if I look at the highest power of x on either side, well, if I multiply out the right-hand side, I would get x squared, right? This is actually x squared minus 6x plus 9. And this is actually x squared minus 3x. So if I equate the coefficients of x squared, I see on the left-hand side, I have a 0x squared. On the right-hand side, I would have an a times x squared. I would not have a b times x squared, but I would have a c times x squared. Or in other words, the coefficient of x squared on the left has to equal the coefficient of x squared on the right. And then since I know that a is -2/9, I can say that 0 equals -2/9 plus c, which means c has to equal +2/9. Alternatively, if you don't like that, Although I don't recommend it because if there are lots of things to solve for, really equation coefficients is usually the more streamlined way of doing this. You can pick a different value for x. So for example, you could say, I'm going to pick something I haven't chosen. So I picked 0 and 3. I'm going to now pick x equal to usually something small, like 1 or 2 or negative. So I pick x equal to 1 and plug it in and also plug in my values for a and b. I have 3 times 1 minus 2 equal to -2/9 times 1 minus 3 squared plus 7/3 times 1 plus c times 1 times 1 minus 3, which just looks kind of gross. I mean, it'll work. 3 minus 2 is 1. -2/9 times 1 minus 3 is -2 squared is 4. -2/9 times 4 is -8/9. Plus, I'm going to change this to 9. So 7/3 into 9 times 3 over 3 is 21/9 equals c times 1 times -2. So, oh, sorry, not equals plus -2c. So then bringing everything to the, let's bring the c to the left side. We're going to have 2c on the left, and -8 plus 21 is 13/9. And then -1 is -9/9. So I get, right, just it seems kind of awful. So C2c equals 4/9. So c is equal to 1/2 and 4/9, which is 2/9. We do get the same result, it just seems worse. So do what you want, but I would always recommend first I should say, do what you want after you have used your convenient values. Always do this, and then if you prefer, you can plug in values of x to different things, or you can put coefficients, which is what I would recommend. So then we go back to our integral. We're going to be integrating. We're having a three. Yeah, so we're going to do the integral now of, instead of this, a over x plus b over x minus 3 squared. Or that would think of it 7/3 times x minus 3 to the -2. And then c, which is 2/9. That's going to equal -2/9 natural log of the absolute value of x. And then the integral of x minus 3 to the -2, if x minus 3 is the -1st divided by -1. We get plus 7/3 x minus 3 to the -1 over -1. I would simplify this as -7/3 times 1 over x minus 3, or -7 over 3 times x minus 3. And then finally, plus 2/9 natural log of x minus 3. Let's see. Yeah. One more partial fraction problem. There's lots of stuff to say about partial fractions, but you can only say so much. And this video is going to be kind of long. Let's look at one more example. The integral of, hopefully I've done this right, 8x squared plus 2x plus 3 over x to the 4th plus x squared. So again, u sub is out. The bottom is the higher power than the higher degree than the top, and the bottom is factored. So we're going to rewrite this 8x squared plus 2x plus 3 over x squared times x squared plus 1. So the x squared is a repeated linear factor. It's x minus 0 following the square. So I'm going to have an a over x squared, a b over x. And then the x squared plus 1 is what's called an irreducible quadratic factor, right? That parabola doesn't cross the x-axis, or if you hit it equal to 0, there are no solutions, or it doesn't factor. That's going to be cx plus d over x squared plus 1. And then we multiply both sides by the common denominator. So we're going to get 8x squared plus 2x plus 3 equal to a times x squared plus 1 plus b times x squared plus 1 plus cx plus d times x squared. If you prefer, you might multiply this out a little bit. You might write this as ax squared plus a plus bx cubed plus bx plus cx cubed plus dx squared. You might not. I don't know. Either way, I'm still going to use, well, I only have one nice value of x here. I only have x equals 0. If I plug in x equals 0, I get 3 on the left, and then I get I would look at this really. I don't want to look at this yet. I would get a times 1 plus b times 0 plus c for b times 0. So a equals 3. Great. And now I'm going to equate coefficients. So I'm going to look, well, the highest power of x is actually x to the third. So if I look at x to the third, on the left, I have a 0, x to the third. On the right, I have a b times x to the third, and I have a c times x to the third. So multiplying it out like this kind of does help to see what the coefficient should be. If I looked here, I'd be like, okay, well, I don't have an a times x cubed, but I do have a b times x times x squared, or that's a b x cubed and a c times x times x squared. I don't know b or c, so I keep going. I look at the next highest power, which is x squared. On the left-hand side, I have an 8x squared. On the right-hand side, I have an a plus d. But I know that a is 3. So I can say that 8 equals 3 plus d, so d equals 5. Great. Let's look at x. On the left-hand side, I have a 2x. On the right-hand side, I have a b times x. And that's actually it. Right? There's no other coefficient of x. So b equals 2. And then I can plug that back in over here to get that c must equal -2. Cool. So then we can rewrite our integral as the integral of a over x squared plus b over x plus cx plus d, so -2x plus 5 all over x squared plus 1. You want to always break, if you have something over x squared plus 1 or x squared plus whatever, you always want to break that up. I want to write that as, first I'm going to write this as 3x to the -2 plus 2 over x, and then I have a minus 2x over x squared plus 1, and a plus 5 over x squared plus 1. That's going to equaling 3x to the -1 over -1, or -3 over x plus 2 natural log of x. The value of x, the integral of 2x over x squared plus 1 is a quick use of, it's going to be the natural log of the absolute value of x squared plus 1. And the integral of 5 over x squared plus 1 is going to be 5 arc tangent. There's a lot of things to cover here. I'm going to run out of time. Okay, let's see. So what's next? Oh man, yeah. So I think that's a good stopping place here. So, but we're not through all the tricks. So I will come back and do the rest of the tricks, and then talk about trig stuff, and maybe there's my parts in part 2. I guess, yeah, I have time for, I guess I have time for the third trick. So trick 3, completing the square. Which is also going to come up in trig substitution. So specifically, if you have something like the integral of 1 over x squared plus 10x plus 34. You can write that as the integral of 1 over x squared plus 10x. And then to complete the square for x plus 10x, you say, well, 10 divided by 2 is 5, 5 squared is 25. So you want a 25 there. The reason you want a 25 there is because this is going to factor as x plus 5 squared. And then you can either say minus 25 plus 34, or just realize that 34 minus 25 is 9. And you like doing this way, it probably is a little bit easier to imagine. So then we're going to get the integral of 1 over x plus 5 squared. Minus 25 plus 34 is plus 9. And there's a number of ways to go about doing this. Yeah, sure. The 9 there is a little challenging. You could do the thing where you factor out a 1/9. Let's say it's going to be the integral of 1 over x plus 5 squared over 9 plus 1. And then rewrite this as the integral of 1 over x plus 5 over 3 squared plus 1. And then you let u equal the stuff that's being squared. So u is x plus 5 over 3, or 1/3 x plus 5/3. And the du is just 1/3 dx. So 3 equals dx. So this integral becomes the integral of 1/9 integral of 3 du over u squared plus 1, which is really 3 times 1/9. And the integral of 1 over u squared plus 1 is the arc tangent of u. That becomes then 1/3 arc tangent. X will probably listen. To be honest, though, if I were doing this problem, I would have gotten to right here and seeing that I had the integral of 1 over something squared plus something squared. And that's going to be basically, that's the thing. You get a 1/3 arc tangent of that divided by that. That's kind of all right. I will stop there and I will complete the rest of this later.